Hello, my name's Sophia, and here's a little bit about my research at the University of Arizona's CAT Vehicle REU program. Before going into the details of my research project, I'll start with some background. I'll be a junior this fall at the University of Oregon and am majoring in data science with minors in math and environmental studies. I applied to CAT Vehicle so I could get some hands-on experience with convolutional neural networks, and also so I could try out their self-driving car. Sadly, my second wish did not come true thanks to Ms. Corona, but I still had a really great team. There were 7 of us spread across the country, and luckily it ended up being that my partner Anna and I would both be in Oregon for the summer, so we were able to meet up the last few weeks. Our mentor Armindo was in Tucson, and together we were the Cat Ladies. I tried to snag a picture, but the best I could get was us laughing at how much more photogenic Armindo was than Anna and I. Anyways, the heart of our task was to create an SQL database for autonomous vehicle researchers. Every time someone conducts a test drive, a lot of data is collected, like dashcam videos, GPS information, and CAN bus messages. Right now, all of this data is stored in cybers, all jumbled together, and it's nearly impossible to locate specific files. With all this information organized in a database, you can easily search for drives with specific environment criteria to train a car under a variety of circumstances. Anna was responsible for the creation of the database, and I was responsible for preparing the data to go into it. So if you want to know more about the tables and database structure, definitely check out her video. Prepping the data had 2 parts: cleaning the CAN messages and performing object detection on the dashcam videos. The CAN messages contain signals like speed, lead distance, and cruise control state. The object detection tells you when things like other cars, traffic lights, or people appear during the drive. For the object detection, we use the YOLO v5 network pre-trained on the popular Common Objects in Context dataset, COCO for short. YOLO is a single-stage detector, meaning it predicts objectness scores and class probabilities simultaneously and is crazy fast, which is why we picked it. Still, running YOLO v5 on all the drive videos would require a lot of computational power, so I used UA's HPC instead of my MacBook. On the HPC, the inference speed was about 8 milliseconds, several hundred times faster than my laptop. The end result looks something like this, along with a CSV file with all class predictions per frame to be stored in the database. The model's really good at detecting key classes like the ones I mentioned earlier, but there is the occasional false positive, particularly with smaller objects. COCO has 80 classes, which is more than necessary for our purposes, but we liked the wide range of classes because it allows for more flexible queries. Increasing the confidence threshold to 0.5 helped suppress some of these false positives. Finally, the last step was to combine the object detection results with the radar traces recorded during the drive. The radar signals are part of the CAN messages and provide information about other nearby objects' location and speed. The idea is that if the radar system detects something during a test drive, the object detection performed on the dashcam video can identify what that object was. And if we can document which objects appeared during the drive, and when and where, then it's possible to recreate the drive later on a simulator. There wasn't enough time to explore this super extensively, but after filtering radar traces for one of the drives, we found that it's possible to locate times in the dashcam video when an object comes within 10 meters in front of the car, and to identify the class of that object. The lateral distance threshold was set to 1 meter, since the car is roughly 2 meters wide. For example, here's the exact moment when an object is detected within that 10 by 2 meter threshold. On the video, this 10 by 2 meter plane looks like a trapezoid. To determine which object is in this region, if any, we use the bounding boxes predicted by YOLO and check to see if one of the lower corners is within the bounds of the trapezoid. As you might guess, for most of the objects that appear during a drive, this object is another vehicle, although it is nice to know that it happens to be a car rather than a truck or a bus. This moment also happens to be especially interesting since it's the beginning of a cut-in. Here's an example when the object is something other than another car. Right now we're mid-turn when the radar picks something up, and by following the same steps we determine it's a fire hydrant. Here's one last example, except this time we can see that there's actually nothing in front of us. Rather, the radar is most likely picking up the overpass above, which we don't care about all too much. So in this case, the object detection helps us conclude that there actually is no object. And that pretty much sums up our project. I learned a lot about the architecture of object detection frameworks and also things I hadn't thought of before, like using GitHub to collaborate and LaTeX to write the paper. Even though the program was remote this year, I still had a really great experience and would definitely recommend it to anyone who's agonizing over doing research or industry like I was when I applied. I'd say my biggest takeaway is that I feel a lot more confident thinking about grad school now that I got the chance to try out the day-to-day research process and find out that it's something I actually enjoy doing. So thank you so much to everyone that made this program possible, and thanks for watching.